Hey class. So the exam is next Tuesday, the final exam for the course. I will post it online on e-learning, and you'll have a week to complete it, the same as the other exams. And that'll be it. I do intend to post lectures for next Tuesday and Thursday, and much like we've done for the second half of the semester. Um, it's not strictly going to focus on things that you might be tested on, more so on uh, things that will hopefully help you down the line as part of your career. Uh, so I will go ahead and have those lectures. I don't know yet, whether or not I'm going to also give you the answers to this exam. I would bet not, since I feel like I've kind of already given you the answers for the first two, and in doing so, prepared you for this third one, or so is the hope. But if as I'm reviewing it, if it feels like it's unfair, then we'll go back and do that. So we'll continue on with the discussion of the zeta function today and its behavior in the critical strip, and another way to look at showing where the non-trivial zeros are for that function. And then, if we have time at the end, which I suspect we probably will, this is a somewhat shorter proof, then we will just have a freestyle discussion, I guess, on various topics. So, okay, let's jump into it. Okay. So we've kind of already been looking at it, and we know that complex functions or complex valued functions take as input a complex number, which is composed of a real part and an imaginary part, or a real part and a lateral component, or a complex component, whatever you want to call it, a thing that gets multiplied by a square root of -1. And so we'll use throughout this proof, we'll use sigma to mean the real part of the input variable, and t to use the complex component of the input variable. But as you'll see, when we're manipulating it and we're setting up the problem, that these will get moved around, sigma and t will, so that you just have to remember that sigma represented the original real part of S, and then t was the complex input. And so by hypothesis, all of the points where this function will be 0 will lie on the part where sigma is equal to 1/2, and then t is really going to vary from 0 on up to infinity. And in a while, you'll see why we don't consider 0 to -infinity. And we do, but we've essentially folded the input space. We folded it a couple times, actually, so that we can simplify our discussion. Right? And we'll talk about down here why that was a fair thing to do. So I gave you the full functional equation for the zeta function, and this is that part of zeta of 1 minus s that I was talking about, where if you want to know something with negative sigma, right, where the negative real part as the input variable, then you'll actually end up computing 1 minus s, zeta of 1 minus s, and then multiplying it by this stuff, right? And there are a few simplifications, such as because of this component, we know that anytime that s has only is purely a real variable, has imaginary component of 0, then this is going to be a multiple of pi whenever s is an integer multiple of 2. But we know that doesn't hold for s equals 0 and larger real values. So this component ends up only providing those trivial zeros at the negative integer inputs. So there's this factor. And why not the positive values? Well, this one, this reflection of gamma, ends up providing a sequence of infinities that offset this, right? So we call them poles in complex analysis. So it has these everywhere that s is a negative, I think just a negative integer, then we're going to end up getting a value which offsets this one, right? Right, so that if s is positive, or has a real part which is positive, then this would potentially be negative. And whenever this would provide a zero, it resolves and disappears, right? These two cancel out. So that's the logic behind what happens to all of those zeros to the right side of s equals 1, right? Is that they get resolved by the poles of gamma. Okay, so it's definitely not clear what's going on here. We know that this is just a constant value, and these are functions, but these are both special functions, and this is something that the average person hasn't really studied, moving up the complex plane. So it's intimidating. It's a bit intimidating to consider. But there are certain properties that we can observe. So the zeta function has conjugate symmetry about the real axis. What that means is that if you flip the sign of this on the input, right, so that you go from s equals sigma plus it to s conjugate, right, this one with the bar above it, we call that conjugate. So s conjugate is equal to sigma minus it. Right? So that's the relationship between a variable and its conjugate partner. So you flip the sign of the imaginary component. Right? And so when you do that on the input variable, the result ends up getting flipped. It passes straight through everywhere else, and so the output value is also the conjugate of its unconjugated partner, right, of the original variable s. Right? So from the functional equation above, from up here, we have this symmetry of zeros within the critical strip, and that symmetry occurs about the critical line. That is when sigma is equal to 1/2. So if we have one value, where zeta of s is 0, and we looked at a few, right, 14 point something, 21 point something, where our Euler product and the value we derived from the eta function, where those resulted in a value that was in our program that was really close to 0, but in actuality there is a point a point with some irrational value of t for which that value is 0, but we know it's in the neighborhood of that. Anyway, so we know kind of what they look like and how to compute them. We've written a program to do so. And so we have this additional property that whenever this value is 0, so if you have one value which is 0, if you reflect it across the critical line, then you get another value of 0. So there's this symmetry, right? And the reason is right here, right? So if this was 0, right, well, none of this is 0, right? We know that none of these are constants. This is the sine function, which is known not to be 0 in the critical strip. And this is the gamma function, which is known not to be 0 anywhere. I think it's nowhere 0. Like, it's either undefined, so it shoots off to infinity at certain points, or it has some finite value, some finite non-zero value. And so if this is 0, well, something on the right-hand side has to take this all to 0. And so that thing turns out to be this, right? But this is every bit as frustrating as whenever you're looking a word up in the dictionary and and that same word appears in the definition. Right? Like, how it's not helpful. I already didn't know what I was looking at. So giving it back to me with all of this other, we won't call it garbage, but all of this other additional information which does not simplify the problem, doesn't help at all, right? But we do know that because none of this is 0, that whenever this is 0 in the critical strip, this must also be 0. Right? We know that from the functional equation. And so we get this, right? So we have symmetry about the real axis, and we have symmetry about the critical line. So we combine those two observations, and we see that the non-trivial zeros, the ones that are in that region we discussed on Tuesday, will have, each time we encounter some value t, right, which for the input variable, which satisfies the equation zeta of s equals 0, that there's going to be either 2 or 4 zeros associated to it. So because of this, right, if we have some solution where zeta of s is equal to 0, then we're also going to have this conjugate one, where by flipping the sign of it, right, so going from sigma plus it to sigma minus it is the input variable, like represented by this, right? Well, if this is 0, then its conjugate value is also going to be 0, right? So if we find 1, then we've really found 2. One on the top half of the plane and one on the bottom half plane, right? So it's sufficient to only consider the top half plane. But because of this, right, this symmetry about the critical line, if we find 1 here, then we've either, well, if sigma is 1/2, then it's just 1 new 0, right? But if sigma is anything other than 1/2, then it's 2. It's 1/2 plus, some delta, and 1/2 minus some delta. Right? And then there's also, well, if these turn out to not be the same thing, well, actually, I think it would be this one and this one, right? If those turn out to not be the same value, if the conjugate of 1 minus s is not equal to s, which is the case whenever sigma is not 1/2, right? So basically we're saying if we found one off the real line, then because of this symmetry about the critical line, then we will have found 2, and then because of this one, it'll double to 4. Right? So the conjugate of that derived 0 would also be a 0. Right? So if it's on the critical line, then each time we find 1 0, we found 2, one on the top half and one on the bottom half. And if it's off the critical line, then each time we find 1, we found 4. Right? So it's a question of how many exceptions there are to finding these non-trivial zeros off of the critical line. Okay, so sigma equal to 1/2 turns out to be really important, and we're just restating here that that whenever it's on the critical line, it represents 2 zeros. Right? Okay, so the function has this definition for, so zeta of s is also really the product of gamma of s and zeta of s is shown to equal I divided by 2 times the sine of pi s or whatever, but it can also be put in this form, right? So it's I times the contour integral of this times dz, and again we can generate this, and so this product has removable singularities at all the integer values of s less than or equal to 1. Okay? And that's because these are canceling each other out. This goes to 0 whenever this goes to infinity, and so they cancel each other out. And so the integer inputs for s greater than or equal to a result of the factor, yada yada yada. And so all of the other zeros occur within the critical strip. And so again, this is 0 nowhere. And this is only 0 for certain values on the real line, and even sometimes when sine of pi s is 0, gamma of s cancels it out. So that's all this is saying. So then everything else is going to be the zeros of zeta of s, and so this is going to inherit those non-trivial zeros because this is multiplication, and anything times 0 is 0, right? So this is forcing because this is a product. When this is 0. There's nothing to cancel it out. There's no infinity factor of infinity to resolve it to some constant. So then this must be 0 for all of those non-trivial zeros. Right? So we're going to hammer away at this. So the contour that we choose is not so relevant. It really doesn't matter because the singularity happens whenever e to the z, so this variable of integration, whenever z is equal to 0, and this becomes 1, or e to the 0, so it becomes division by 1 minus 1, which is 0. And so there's this simple pole right there at the origin. And so we can use a theorem from complex analysis tells us that we can use really whatever contour we choose, whatever turns out to be convenient from us. So we're going to choose the unit circle to integrate around the origin, right? And because there's a singularity, that will be sufficient to properly represent the function because we're integrating around that pole. Right? So we do have to avoid multiples of 2 pi I along the imaginary axis. And so the branch that we're going to choose is going to be defined. So rather than starting at 0 and then circling around and going back to 2 pi, we start at negative pi and then we circle around and go to pi. Okay? So that the imaginary part of the log of negative z is between these, right? So the argument, right, of negative z is going to lie between these. Okay, so now we're going to redefine the contour integral, and this is the same thing that you'll see in calculus whenever you define contour integrals in calculus. So you have some contour and you draw it, and then you have to integrate along that path. So you replace this notation by substituting a function for your variable. So your function, or this variable of integration, right? We don't have these beginning and end points like you're probably familiar with when you're dealing with the contour integral. You have a starting point and an ending point. And so the convention is to define this function, gamma of, in this case, gamma of omega, as equal to e to the I omega, right? So the contour we're drawing is going to be the unit circle, and so this is that unit circle. Right? And then we give omega the boundaries that we wanted, right, that we'd specified up here. And so then we begin substituting. So everywhere that you see z, the variable z, the variable of integration, then we're going to replace it with our function gamma of omega. Right? And then the contour notation gives way to the one with beginning and end, or end points, or our finite integral, our definite integral. Okay, so the first thing we do is we separate out this negative 1 from inside here. So it's still going to inherit the exponentiation, but we can now do something with it, right? So we just move it to the side, and we'll consider it in due course. And then, like I said, everywhere that you see z, whenever you're doing a contour integral, once you've defined the contour, then you replace it with the function that maps out the contour. And so e to the iw replaces the variable of integration, e to the iw replaces the variable of integration, and so the derivative of our function dz, right, is going to be this, right? So derivative of the exponential e to the x is going to be e to the x dx. So in this case, it's e to the I omega d I omega. Well, and that's I, right? And then we have this new variable of integration, right? So this is just the substitution step where we've replaced z algebraically. We've just gone in and replaced z with this, right? And then now we have a definite integral range, which is evaluated from negative pi to pi. and it's essentially we're changing the argument of the complex variable in order to draw this circle. Right? Okay, and then this is another simplifying step. So -1, we've looked at a way to represent it as e to the I pi, but it's well, e to the I theta is cosine theta plus I sine theta. And so whenever the real part is -1, then the cosine of theta part has to be -1. Right? And so that happens at pi plus multiples of 2 pi. So at pi, -pi, 3 pi, -3 pi, and so on and so forth. Right? So there's an infinite number where that could be. In particular, both of our endpoints are potential candidates for generating values of -1. So for now, we just leave this shorthand as this value is represented by some e to the I times the log of -1. We don't know what argument we're going to use, but we'll get rid of it here in a second. And then it's still raised to that power. And so now we have this stuff outside the integral, which we'll take a look at, and then this stuff inside the integral, which is now a definite integral. Okay, so that term which is sitting in front of the integral and causing us distress, it contributes nothing really to anything in the critical strip, but it confuses the problem a bit. So we don't want to just dismiss it. So we want to do something interesting, right? So let's consider these in pairs in terms of conjugate choices for what we're going to do with the log of -1. So one time we'll consider every possibility kind of simultaneously, right? So it can be pi, or it can be -pi, or it can be 3 pi or -3 pi. And whichever pair you choose for the log of -1, in this case we're going to choose -pi and pi. Then if you were to take the product of those results and then take the square root, right? So this is something we call the geometric mean, right? So a times b, the square root of a times b is the geometric mean of two lengths. Right? So if we do that here, right? So in one it's pi, and in the other it's -pi, and we multiply them together, and then we take the square root. Well, the result is just going to be whatever was inside this integral. So essentially, all things considered, quite literally, if we consider all possibilities for this and we take an average of it, well then this variable just disappears, right? And so this is the average of all of the possible choices for how you resolve the log of -1. And it's pretty beautiful because it gets rid of this funky exponent as well. So this all drops off as a result of that. And so we can look at just this. It simplifies to just this, which is really nice. Okay. So assume there exists some zero, which is in the critical strip but not on the critical line. Right? And you have some value t greater than 0. So then by all of the symmetries that we were looking at before, right, then there's going to be this complementary 0, right? The one that's reflected across the critical line. So if you had a 0 at sigma plus it, then you would get one at 1 minus sigma plus it. So if sigma was 1/4, right, then you would have a 0 at 1/4, at real part of 1/4 plus it, and then at real part of 3/4 plus it, right, because of that symmetry. Okay, so then both zeta of s and zeta of s complement, right, if they're both 0, and that's logically equivalent to saying that they're equal, right? If they're both 0, then they're equal to each other, right? And that is logically equivalent to saying that their difference is 0 at those points, right? So that there's no distinction between sigma equal to 1/4 and 1 minus sigma equal to 3/4. Right? They evaluate to the same output. Right? There's no distinction between these values. Okay, so now we have something that we can sort of pry on. Okay, since all non-trivial zeros for zeta of s in the domain sigma between 0 and 1 are given by the integral this, right? Then here we expand s to be sigma plus it, so we can start manipulating it a bit. Then we say that that's the same thing, by this logic here, right? They must equal each other, right? S and S complement. So here you have S, and here you have S complement, right? And so we're putting it in this form. We're subtracting them, and then we're going to merge them, right? And we can do that because the integral, the integrand, converges. It converges over this range, converges everywhere. So to advance further, we have to combine them. Right? So we've now represented this by this. Right? And then now we combine them into a single one. So they have a common denominator, they have common endpoints. It actually turns out to be really simple to combine them. And now we multiply it out, right? So we separate, we bring this down so that it's I omega times sigma plus it. And if you multiply it out, then you end up with e to the omega t times e to the I omega sigma, right? So this is going to be your modulus, and then this is going to determine sort of the angle that your line comes out from the origin. Right? Or this deals with the argument of it. And then again, something similar, e to the negative omega t times e to the I omega 1 minus sigma. Right? Well, this had e to the negative omega t, and this had e to the negative omega t. So we're going to pull that out in front. So now we have this these 2 points on the unit circle, and we're measuring the difference between them. So that is the idea of a chord, essentially, right? A line which passes through a circle at 2 points. So this is 1 point on the unit circle, and this is another point on the unit circle. And as we integrate, as we allow omega to vary, these points kind of race around and chase each other. But their length is never more than the diameter of the circle. Well, it's the unit circle, so the diameter is 2. Right? It has radius 1 and diameter 2. So it's never more than 2, and it's never less than 0 in terms of absolute value. So this is finite, readily understood. This is the same thing every time. It doesn't matter what the inputs are. Right? This doesn't vary with respect to sigma or with respect to t. The denominator just has this path that it follows as omega ranges from negative pi to pi. So that's fairly regular. And then out here we have this exponential decay. So as t goes off to infinity, and as it ranges from 0 to infinity, this is going to get smaller and smaller. And so this is going to dominate this, which is bound between 0 and 2 in terms of absolute value, and this, which is bound between, I forget. It's something like 1.5 and 2.5 or something like that. We'll look at it here in a little bit. Right? And so this is not so bad to work with. And so we'll take a look at it. Okay. So this again just says what I just said, right? So there's that decay at the front, and it decreases both as we range from the beginning of the integral, right, the start, towards the end, and then it also decays with respect to increasing t. Right. Okay, sure. So this kind of motivates what we're going to try and do. So because of the symmetries that we've already discussed, we can restrict our consideration of the critical strip to just the values between 1/2 and 1, right? Because if we find one in this domain, right, where sigma is between 1/2 and 1, then we're guaranteed to find one between 0 and 1/2, with the one exception being if it's on the critical line. We'd still find one, if it was a closed interval at 1/2, except that it would be identical to this one, right? It's on the critical line. So then there's the critical line itself, sigma equals 1/2, and then everything else in this in this range between 1/2 and 1. Okay, well, whenever sigma is 1/2, then the integral representing our difference of sums. Right? So these are this is a difference of integrals that we've simplified to this form. Okay? It becomes identically 0, right? So you just plug in sigma equals 1/2, and you get this and this. Well, this reduces to 1/2. So then this is always 0, right? So then this is always 0. So that's as you would expect. If you perform the same integral twice, you would expect to get the same value twice. And so the difference should always be 0. Right? Everywhere else, right, then when you plug it in, you can split the integral into a head, right? Because this is decay, so it's going to be a function which decays, right? So it goes down like this. In terms of absolute value, it's just this rapid decay, right? Rapid exponential decay. And so everywhere that it's really far from 0, like if you were to integrate that function, then most of the value of the integral would happen right here, right at the beginning of the integral. And so that's the spirit of what we're going to try and prove. Right? So there's that part that we can make statements about, and then everything else that we just don't care about because it's too small by the time it comes up. So we're going to choose omega in the range, or in the domain of negative pi to negative pi over 2, and then the last 3/4 of its domain from negative pi over 2 to pi will be the tail. Right? So most of what we need will happen within this these values for omega, and then everything else we can show to be dismissible. Okay, so now we have this, right? And so we're splitting up this integral, right? Just the terminal points, the beginning and the end, as defined. So into a head, right, where it ranges from negative pi to negative pi over 2, and then a tail where omega ranges from negative pi over 2 to pi. Right? Okay, so it still looks kind of complicated, right? So what can we do to simplify it? What can we do to take it from something complicated like this to something simple like this or this? So just following the rules, right? E to the I theta equals cosine of theta plus sine theta. Right? So e to the I omega equals cosine of omega plus I sine omega. Right? And then, well, in the exponentials, if you have some addition, then it's really, you can separate it into multiplication, where the first summed is the exponent of that base value here, and then the second factor has the second exponential summed. Right? So this breaks into cosine plus I sine. Right? So we do that step here, and then while this is still e to the I sine of omega, so again it breaks into cosine plus sine, but sine omega is in the exponent, right? So that becomes the input variable for cosine here. So, and then there's the plus I sine, right? So that comes in over here. So sine of sine omega. So we have this composite function call. And so this, if you take the modulus, and if you look at the absolute value of this complex variable, or complex valued function, then the modulus is just the same as the Pythagorean Theorem, right, where we have a value for x and a value for y. Right? So x squared plus y squared, and then you take the square root of their sum. Right? So that's what this is. Right? So that's the modulus of it, and that's exact. Right? And that is independent of your choice of sigma and your choice of t. Right? That's just moving with the variable of integration. Okay, so for any choice omega, right, the modulus is bounded between 2 and 1/2, and I'll leave you to verify it. But you can let it vary. I mean, the input domain is finite. It ranges from negative pi to positive pi. Right? So you can just graph this function, or the absolute value of this function. And you can see that the modulus is bounded by this. And so it's minimal whenever omega is some odd value of a multiple of pi. So pi, 3 pi, 5 pi, etc. And it's maximal whenever it's an even multiple of pi. So 0, 2 pi, 4 pi, etc. Okay. So we're trying to split this into a head and a tail. And the reason that we want to do that is because we're measuring a difference, right? And so we want to say that this function can never be 0 except when it's on the critical line. So for the critical line, we've already shown that the difference between zeta of s and zeta of s complement is always 0 because it's in that left half and the right half of the critical strip. But for everything else, the difference between zeta of s and zeta of s complement should be non-zero. And so we're using exponential decay to show that. And we're going to say that that difference, there's a difference when you first start integrating, right? Whenever you integrate just over this range, omega between negative pi and negative pi over 2, that this is non-zero, right? And it's a little bit complicated at first, or it's new. It's something that you kind of have to get used to. The idea that we can make statements about the absolute values of this and say that, well, we don't know everything about this, but we know that the absolute value of this in total is going to be greater than if we considered only the real part. And that's from the triangle inequality. Right? So the absolute value is going to be the square root of the real part squared plus the imaginary part squared. If it's purely real, then we know that the absolute value is exactly equal to the real part. If it's purely imaginary, then it's still greater than the real part, which would be 0 in that case. And so if it's anything in between, then the statement holds, where the modulus of it, the absolute value of that complex value, is going to be greater than the real part. And again, it's just because of the triangle inequality. And so we say that real part can act as a lower bound for the modulus of this, for the absolute value of this. Right? So that we have, this has some modulus, which is greater than the real part of the output of this. Right? And that real part, so something that is even smaller than this, is always larger than however big you can imagine this part to be defined over this input domain. Right? So that's what we're trying to show. So the head is bigger than the tail always. And when that's the case, then this, because this is bigger than this, so to speak, then when you add them together, you never get 0, right? Because they would have to be opposite in sign, right? And then they would have to be equal in magnitude. But because they're never equal in magnitude, it doesn't matter if they're opposite in sign. It doesn't matter what this does. This will never be 0. Okay? So that's the spirit of what we're trying to show. And so we have to jump through a few hoops to get there. Okay? Okay, so we're trying to establish upper bounds and lower bounds. Upper bounds for the tail, lower bounds for the head, and show that narrate the two shall meet. And so sigma in all of this will have extreme values at sigma equals 1/2 and sigma equals 1. And so as we go to 1/2, this we would expect, well, we know that the numerator goes to 0. Right? But we want to make statements about the modulus of the numerator. So we start with this, then we put it into its Pythagorean form. And so once we carry out the multiplications, we end up with this, and then we add 1 and 1, we simplify, continue to simplify, eventually we replace this, this plus its conjugate, right, is going to equal twice the real part. And so we end up with this as the final form. So this is the magnitude, or the modulus of that numerator, the length of the chord, the line segment which passes through the unit circle at 2 points. Okay, so to simplify the denominator, in our estimate, we're going to look at the extreme values. We're going to look at a lower bound and an upper bound. Right? So we consider the lower bound of the modulus of the denominator whenever we're looking at the tail, because we want it to divide by a value. We want it to divide by the smallest possible value so as to maximize the potential value of the tail. And then for the head, we do the opposite. We want to be as critical as possible of the length of those head values so that we can make the strongest statements possible. And in that case, we would reach for the longest possible modulus. Okay, so we know that the modulus of the denominator is bounded below by 1/2. So then, now whenever we look at this part, the magnitude of this, right, of the chord divided by whatever's going on in the denominator, is always going to be less than if we're as generous as possible. So here, right, this is just the magnitude. We haven't done anything but algebraic substitution. We put this part in a different form. And here, we actually have done something. We've said that we're only going to consider this when it's at its smallest, so as to find something that is always larger than this throughout the integral. So throughout the integral, this is an upper bound for this. Right? And it has the added benefit that this is a real value. Okay. So then, this is exactly equal to this. So we just move the 2 up. We can factor out a 2 from inside the square root. So we get this constant 2 square root of 2 times what's left behind. So 1 minus cosine of omega times 2 sigma minus 1. Okay, so now with respect to omega, our variable of integration, then the value is maximal when omega times 2 sigma minus 1 is furthest from the origin. That is, whenever omega is plus or minus pi. So for any choice sigma, the integrand of the tail is bounded above. Right? So we have an upper bound, basically, for the tail, for the part that we hope to show is irrelevant. We're maximizing it. We're making it as large as possible and then picking something even larger than that. So we can say it never achieves a length, an absolute value greater than this. Right? So we begin with the absolute value signs on the outside. We say that the absolute value of whatever's going on with this integral is always smaller than 2 square root of 2 times the integral of this. Right? And so it comes from this statement. Right? So we have the exponential decay, and then we have that fraction that we were looking at before. The denominator, which is always there, and the chord, the line segment, which intersects the unit circle at 2 points. And so this simplifies. But this doesn't depend, we've simplified this to the point that we've removed omega. Right? So we tried to maximize it, and we chose a value where this was maximal, where this part was maximal. So we found an upper bound for it. So we replaced it with this, right? And now we can integrate omega, right? Because omega is no longer in here. We found some upper bound for it. And so this integrates. We can find some value for this, which is fantastic. So we do that integration, and it comes out like this, and then we can evaluate it. And so we know that once you evaluate it, you end up with this. So something which depends on sigma and t, right? And so now we're going to look for something in the integral of the head part, which also depends on sigma and t. And then we can make statements about whether or not, and then we can test the veracity of our statement that the head always has a modulus which is larger than the modulus of the tail as we've defined them. Okay, so we complete the proof by establishing a lower bound for the real part of the head and demonstrating that this diminished lower bound is still greater than the upper bound of the tail provided. Right? So for the tail, we were as optimistic as possible. For the head, we're going to be as pessimistic as possible, while still being generating allowances that are close enough to what the true value is, so as to still allow us to prove the result. So to establish a lower bound for the real part of the head, we have to account for the argument and the denominator. So observe that this, again, we're going back to the fraction, right? Becomes this when you expand to the denominator, becomes this. Well, the denominator is a complex value, right? And complex values are modulus, right? So it's an absolute value. It's some ray coming out from the origin, and then it's rotated at some angle, right? Where this is the angle. But here, because it's in the denominator, it's moving in the other direction. So here it was e to the I theta when it was in the denominator, but because of the rules of fractions and everything, because it was in the denominator, e to the I theta becomes e to the minus I theta, or in this case, e to the minus I times the argument of the e to the cosine of omega times e to the I sine omega minus 1. Okay, so then this gets expanded, right? So we multiply this through in the numerator, right? So we move it through. And again, it's still a chord, right? And so now we have an absolute value in the denominator. So this is a real value. And we haven't lost our specification because this is carrying the complex argument, right? The angle that it makes with the real axis, with the positive real axis. And the same thing here. And so we've just moved it to the numerator. And so this is still a chord, and then this is some value, some real value. Okay, well, it's in that e to the I omega, or e to the I theta form, right? So we can split it into cosine and sine, right? So we do that, right? And now we've expanded it out quite a bit, but if you go through and do the work, you see that we're just pulling in the arguments here, right? So what's in the exponent here goes here. So this is all real, and this is all imaginary. And so now we look at whenever theta is between negative pi over 2 and pi over 2. Right? So in such a case, right, if we have it bounded, then the argument of rho times e to the I theta is equal to the arctangent of rho sine of theta over rho cosine of theta. So what that's saying is that you can compute the angle, you can compute theta by doing the tangent, right? So this might be simpler to see on the whiteboard. Okay, so this is theta, right? This is your value y, this is your value x, and then this is your modulus, right? So okay. So it's a triangle, right? It's the imaginary part of z, right? The real part of z, and the modulus of it, which is the hypotenuse of the triangle. So this is the square root of x squared plus y squared. Okay. Well, the tangent of theta is the opposite over the adjacent, right? So y over x, and then well, then we just take the inverse trig function, right? So the arctangent of this is going to give you the angle, and the arctangent of this is really how you compute that angle. So that's all we're saying, is that we're going to consider it now in these terms, in terms of trigonometry, and say that it is possible to find that angle, right? And we're going to use the arctangent to do that. Okay, so whenever theta is in that range, then we can just state it as the arctangent, and we find out that the length doesn't really matter. It's just a scalar, right? So we scale it back down, and sine of theta and cosine of theta are really all you need in order to compute this angle theta up here. So arctan is an odd function, so if you negate the input variable, then you negate the result. And so in this case, we know that we're negating the angle, and so that's going to negate the result. Right? And it negates it because of this. Right? So this is cosine of theta, rho times cosine of theta, minus rho times sine of theta. Right? So the imaginary part becomes negative rho sine theta. The real part is still rho cosine theta. And then this passes through. Right? So you get the negative angle, which is correct. Right? You would want the negative angle if you negated the angle. Okay, so now omega, our variable of integration from way back when, so it has, so now we consider it in this form whenever we're looking at the denominator. Right? So the argument of that denominator, right, of e to the cosine omega plus e to the I sine of omega minus 1 is the arctangent of this over this. Right? And so for all complex numbers z, we have this property, which we just discussed, okay? Pythagorean Theorem, real part squared plus imaginary part squared, and that this is always going to be greater than or equal to if we only consider the real part, right? So if we threw this away, and this is always guaranteed to be greater than or equal to 0, then we can make this assertion, right? So this is true. Well then, all this is saying is that this has a lower bound of the real part of z, or the absolute value of the real part of z, I should really say. Okay. So then, well, I guess the statement is true, right? Because if this is negative, it's still true. But it's meaningful that it's true for the absolute value of the real part of z. Okay. So now we're going to take a look, right? So we have just some summation, right? A bunch of terms. We take the absolute value of the result. So you add them all together, and then you take the absolute value after the fact, right? After you've added everything together. So some of these may be negative, some of them may be positive, because we're looking at complex numbers. Some of these may be negative, some of these may be positive, etc. Right? But we're going to apply that result, right? So you break z up into its real part and its imaginary part, and then you can break it up into two sums. Right? Well now, this is the real part, right? All of these add up to compose the real part of z, of whatever this total sum is. All of these add up to compose the imaginary part of whatever all of these added up is. Right? And so this is the real part, and this is the imaginary part, the entire sum. Right? So then we use the Pythagorean Theorem, right, because of absolute value. So we square this, right? We square this, and so by that same statement that we just made, right, that this is going to be larger than if we considered only the real part, and the real part simplifies to this. Right? In the special case that for all of these values that we consider, if the sine of the real part of z of j is equal to the sine of the real part of that first term, so if the real part never changes sign, if it's always strictly positive or always strictly negative, or 0, I guess if it's going to violate that, but if it's always strictly one or strictly the other, then you can make an additional claim. So if the sign never changes for the real part, just the real part, then whenever we make this simplification, right, we go from this and say that that's always at least as large as when you consider only the real part. Well, then we have the added notation that these values, the real part of z of j, is going to be the sine of that real part of z of j times the absolute value of it. So it's always positive or negative, and sine is always 1 or negative 1. So it's 1 when it's positive and negative 1 when it's negative. And we've dealt with sine variables whenever computing products. So then we can consider absolute values of the real part of j, and then this sign, which is common to all terms because it never changes sign. So we're talking about the special case where they all have the same sign for the real part. Okay? So in that very special case, then we can factor it out. We can factor the sign out as just a factor, a common factor that they all share. And they're all equal to whatever the sign of that first term was, because it never changed, right? So we make that substitution from the general zj to that very first one, because they all share that same sign by assumption, right? So then that factors out. We can pull that outside of the summation, right? Well, then at that point, it's a product of terms, right? And we can take the absolute value of this times the absolute value of this. Well, this is always 1 or negative 1, right? So the absolute value of that is 1, right? And so now, in this special case, we were able to simplify it even further and move the absolute value signs inside the integral, or inside the summation, so that we're taking the absolute value term by term, right? So that this is larger than the term by term absolute values of the real parts, in the special case that it never changes sign. Okay, so you can imagine that that's going to come up if we highlighted it. So then we define the integral as the limiting case of some trapezoidal estimation of the area under the curve, right? Basically, we're using the trapezoid rule, right? But it really doesn't matter what rule we use. We're just using something so we can define the integral in terms of a summation. Right? So here's our summation. Here's how we handle the endpoints, yada, yada, yada. Okay, so then now we have something that we actually want, right? So we have E, we're going to consider this as the absolute value of an integral of E to the alpha omega times some complex value Z of omega times d omega, right? Where omega is the variable of integration. So here we put it in terms of the definition of an integral, right? So, one of the pieces of advice was to return to the definition. So here we've returned to the definition of an integral. And we just make these substitutions. So this is the integrand. Everywhere that you had f of t, you now replace f of t with this, right? So f of a, right? A replaces omega. So you get this, but with a everywhere omega was, right? F of b, b replaces it, right? B there, right? So it's one-to-one substitution, right? Okay, and then now we're breaking it up into the real part and the imaginary part. And then now we're going to make that claim that if you drop the imaginary part entirely, then the modulus, then you can develop a lower bound by considering only the real part, right? And again, we still haven't really changed anything. And now we're saying that if it never changes sign, that you can pull the sign out and consider the absolute values of the real parts, just as we were looking at before. And then you can get rid of it entirely. And then this is still the definition of the integral. So we can come back to the definition of the integral. So in the case that this doesn't change sign as omega varies, right, for everything in this range from a to b, right, then you can make this simplification. You can actually move the absolute value signs inside the integral and wrap it around this simplified version of z omega, where we consider only the real values, right? Or in particular, only the absolute value of the real values. Right? So thus, so long as the real part of z omega doesn't change sign, then the modulus of the original integral may be bounded below by the integral with the complex factor z of omega replaced with the factor absolute value of the real part of z of omega. So in this vein, we may construct the lower bound for the head of the integral, our difference of sums, by replacing the complex factor, this, right, that monstrosity, which was again a chord through the unit circle, and then denominator, which varies only with omega, right, with the absolute value of its real component, which is given by this. Right? And so you can verify it by doing all of the e to the I theta equals cosine of theta plus I sine theta simplifications, right, where you move this, right, and you can simplify it. But we've already done all this work, right? So this is equivalent to this, right? Sorry, the real component, the absolute value of the real component of this is this. And so there's an imaginary component which we've thrown away because we don't need it. So because we're establishing a lower bound. So provided that the real component doesn't change sign for all omega with its domain of integration for the head. Right? So when sigma is in the right half of the critical strip and omega is in the domain that we've defined for the head of our integral, then this is equivalent to this, right? Now where we've replaced argument with arctangent, right? And so for a fixed choice sigma, this decreases monotonically with respect to omega, right? So each time you pick some choice sigma, then it decreases with respect to omega. So the factor is minimal right, when you've gone the furthest in your input domain, right, because it's decreasing. So it's maximal here, it's minimal here, so the end point is where it's minimal. So then because we're establishing a lower bound, we go with the minimum value. And so we substitute in, for omega, negative pi over 2, right? So now we've gotten rid of the variable of integration now for the head, right? For the troublesome part of it, well, sorry, we'll come back to it, right? So we've gotten rid of it for the head because this no longer depends on omega. So we've made these simplifications and created this lower bound which does not depend on omega. So now we can integrate it, right? Which even without the absolute value operator is greater than 0 for all sigma in 1/2 to 1, right? So even without the absolute value, this is actually strictly positive, and it's all real, right? It's all a real value. And it's positive, but we have the absolute value signs to emphasize that it's going to be positive. Okay. So then let the numerator be represented by the shorthand constant with respect to omega. Right? So this is really long to write out. So let's just write kappa of sigma. Right? So a thing which depends only on the choice of sigma. Right? So then this, right? So this is what we just replaced. So we are establishing a lower bound by considering just the real part, right? Just the absolute value of the real part of this over omega's domain of definition. And then this, once we expand it out, becomes this, right? So all of these get expanded out. We move the argument up here. We make that arctangent equivalence, whatever. Now we're going to apply the lower bound, which we were talking about, right? So we find the value where this thing is minimal, right? And we use that everywhere, right? So the real part, this part, is minimal whenever omega is equal to negative pi over 2. So we replace omega with negative pi over 2. Okay? And so we've established a lower bound. And then we get the strict statement by getting rid of the denominator. So the denominator is maximal whenever it's 2, right? Whenever its modulus is 2. It's bounded above by the value of 2 strictly. So when this is 2, then it's essentially 1/2, right? So when the denominator is 2, that's the same as saying 1/2. So we simplify it by replacing this with a constant. Specifically whenever it's maximal, so as to minimize the result. Right? So now we can make this statement, and we don't have the denominator to deal with, and we only have omega, our variable of integration, right here on the exponential decay. So we replace this with kappa of omega, or kappa sigma, right? And it doesn't vary with respect to omega, so we can move it out in front of the integral, and now we have this, which is really simple to integrate. So we do that, right? And then we evaluate it, and we have our lower bound for the head. Right? So this, once we evaluate it, comes to this, right? Once we substitute back kappa sigma. And then for sigma in that domain, we have the inequality that the head, the modulus of the head, is strictly greater than the modulus of the tail, right? And we get that result. So we come back to the original for the head, and we say, okay, well, you are bounded below by this, we make the substitution of getting rid of the denominator, and we have all of this in here, and then we evaluate the integral, right? And it's still multiplied by this, and so we're going to have a little bit of this left over. Right? But we've evaluated the integral, and then we say that this is strictly larger than EVI pi over 2 over 2t. Well, I mean, we can work it out. I have a longer version of this document where that is worked out. So I'm not sure why I made that choice. So the t is in the denominator from up here. And then e to the pi t. I'm not sure why I didn't just leave that as e to the pi t minus e to the pi over 2t. Why I chose to represent that as e to the pi over 2t. But it's true, right? We can simplify that. And then, oh, okay, I see. So this is what the claim is, right? So this is our simplification of the head, right? So we have this lower bound for the head. And the head's lower bound is greater than, this is the assertion that we're making, right? We haven't demonstrated it yet. So the head's lower bound is greater than the upper bound, which was this, of the tail, right? So the head goes from negative pi to negative pi over 2, and the tail goes from negative pi over 2 to pi. And the fact that these don't meet, that the lower bound, the lowest estimate for this is always greater than the most optimistic estimate for this, proves the result. So to complete the proof, we need to establish some value t such that once we move up the imaginary axis past some point, that that these two are never able to cancel each other out again, in which case their integral, the integral, could never be 0, which would mean that the critical line, as before, is the only place where the zeta of s is equal to zeta of s complement, which is why we're going through all of this exercise. Okay, so then we relate the lower bound to the head, for the head to the upper bound of the tail, right here we've established, right? So we have this, and all of this was again chosen to be kappa sigma. We say that that is greater than this, right? So we restate it here. And so now we're going to go through a series of statements where we're trying to simplify that. So this part, right, is kappa sigma, and this part. So if we move the 2t from here to over here, right, then the t cancels out over here, the 2 multiplies here, and we get 4 square root. Right? So we've only dealt with the denominator over here. Now we move kappa sigma over, and we will deal with that. And then here we try to make a simplification. Right? So this, e to the pi t minus e to the pi over 2t. Oh, okay, I see what happened. Okay, so then we divide this from this side, right? We divide both sides by this, right? That cancels out here, and it cuts this one in half, right? So we get pi over 2, e to the pi over 2t here, and this becomes minus 1, right? And so that's why it happened over here, right? And so now, well, we add 1 on over here. We add 1 to both sides, and we only have this on the left-hand side, right? So something which depends only on t, and then this on the right-hand side. And so now, whenever this is true, right, whenever t is large enough that this is always true, then we will have established our choice of t. So then we take the log of both sides, right, and then we divide by pi over 2. Right? So dividing by pi over 2 is the same as multiplying by 2 over pi. Right? Times the log of this, right, is going to give you your choice of t. So once this is large enough that this always holds true, then we know what our value of t needs to be larger than. Right? Okay. So then we solve for t by identifying the maximum value for the right-hand side with sigma in that open domain between 1/2 and 1. And so numerical test, right, running it on the computer to get the answer, or to get a hint for the answer, will show that this will happen, that the value tends towards its minimum as sigma goes to 1/2. Right? So restoring the expanded form of kappa sigma, right, replacing kappa sigma with this monstrosity, right, in the equation above, right, we're looking for this equivalence for t, which is equal to this. Okay, so we've got our monstrosity back. So considering the expansion of the fraction within the log, right, so we look at this with this, right? So this is a constant, and this is a constant. And so sigma is, like, we've finally reduced the problem to where we're looking at this with respect to just sigma. But it's still, you know, it's still a lot to behold, right? But we're going to take the series expansion for cosine in the numerator, right? So this is the series expansion for cosine, right, where this is the argument. So when it was cosine of x, this is x. So 1 minus x squared over 2 factorial plus x to the 4, or 4 factorial minus x to the 6 over 6 factorial, and so on and so forth, right? Well, you know, once we've expanded it, we see that the 1's cancel out, and so now we have this, right? So the signs are all flipped, right? And there is no constant up here, so it's x squared over 2 factorial minus x to the 4 over 4 factorial, and so on and so forth. Well, we can factor out one of these, right? That's not so big, and even the square, even the 2 can factor out, so that we end up with this, right? The square root of this, which is squared, well, that just disappears. We get pi times 2 sigma minus 1 over square root of 2, right? Because we factored it all out. And then 1 minus a whole bunch of other stuff, right? Okay. And so for the denominator, we consider this and then this separately, right? So this is the first one, this is the second one. So again, we do the series expansion, we get this. We do the series expansion, we get this. And it's a lot, right? But whenever we perform the ratio, right, we look at it and we've taken the series expansions and we've simplified them to the point that we can. We have this in the numerator and this in the denominator. And we see that, well, this is going to cancel out this, right? And the signs are going to flip. So that, right, so canceling terms in the denominator, we end up with this, right? So this is that first squared term, and then there's another one, and so forth, right? So the 1's cancel out, 1 minus 1, and then negative this minus negative this, right? So it's negative this now plus this, because the sign flipped, right? Negative of a negative, right? So this is just that very first term that didn't cancel out. Okay, so we've got to deal with it, right? So then we have, whenever we've expanded it, right, we have, they're both over 2 factorial. Right? So if we move this to the front, because this is now positive, and this one follows negative, right? So then we have the 1 minus sigma over here, and sigma over here, right? And then everything else. And so whenever we consider that, we see that they're oh, okay. Well, yeah, I believe that's the case, right? This is arctangent squared. Hold on. Okay, so it's this minus arctangent squared minus this. Oh, okay. Sorry. So there's parentheses here that I was ignoring, right? So there's parentheses. So x squared or whatever in the series expansion. Well, this was all x, right? This was all inside of these large parentheses. So that's what's happening here. So if you multiply it out, right, then x minus y all squared, then you get x squared plus y squared, right? And so here, because these are both negative, right? You can factor that out, and you get x squared plus y squared plus 2 times x times y. And so that's all we've done here. We've added them together. And so now we're going to try and group things so we can take a look at it. Right? So pi squared over 2 is in both of them. Right? And then here, for this one, whenever we multiplied it out, we had 1 minus 2 sigma plus sigma squared, and then plus some additional stuff. Right? And then here, right, when we multiply it out, we still have pi over 2 squared, sigma squared, and then some additional stuff. Right? And then some of the other stuff had canceled out, right? Like the arctangent ones had canceled out. And so it actually started to simplify. And so then we still have this pi squared, right? But now we've kind of moved everything together. There's enough in common that we can start to look at that. And so this sigma squared cancels out with this sigma squared. So we have this times just this, right? Because these two canceled out. So we have 1 minus 2 sigma. That's all that's left over. And then all of this other junk. Right? So 1 minus sigma here and pi sigma here. And so, well, pi minus pi sigma minus pi sigma. So that's pi minus 2 pi sigma. Factor out the pi and you get pi times 1 minus 2 sigma. So 1 minus 2 sigma here, 1 minus 2 sigma here. We can factor that out. And again, all of this was in the leading term of the denominator, right? And then every subsequent term as well. So we can actually factor out 1 minus 2 sigma from the denominator. And so now by analysis, right, and by persistent analysis, we see that the ratio doesn't go to infinity, right? So as sigma goes to 0, or as sigma goes to 1/2 in the numerator, 2 times 1/2 goes to 1, and 1 minus 1 goes to 0. So that this goes to 0 in the numerator, and then 1 minus 2 times 1/2, well, 2 times 1/2 is 1. So it goes to 0 in the numerator and the denominator, and it resolves to something that's different than 0 and infinity. So numerical methods, so if you just plug it in the computer and you start computing values really close to 1/2, and then analysis as well, you can see that this is clearly bounded above by 3/2, right? And so this is a loose bound. It's not incredibly close to it. I think it's closer to 1.4 or something like that. Right, so this has an upper bound, this monstrosity of an evaluation. Once you expand it out and go through all of the trouble of factoring out that 1 minus 2 sigma, you find that it does have an upper bound. Right? So then we replace this with its upper bound, right? So we can find some value of t, big T, which satisfies all of those conditions. So we make that substitution for 3/2, right? And it plugs right in, and then you just compute it, right? 2 divided by pi times the natural log of 4 times the square root of 2 times 3/2, all of that plus 1, right? And the natural log of all of that. And you see that t is bounded above by this, right? So that if you chose t as this value as 1.5, then for all little t, for all little t here greater than 1.5, that it's impossible to have a 0 off of the critical line because the where is it? Because zeta of s and zeta of s complement are never equal to each other, right? So their difference, which is what we just computed, right, is never 0 unless sigma is equal to 1/2, right? Because these values are never equal, they can never both simultaneously be 0, which was what we showed up here, right? That they would, s and s complement would have to be 0 at the same time, and that never happens unless you're on the critical line. Okay, so that took every bit as long as I expected it to. Have a great weekend. We'll take the exam next Tuesday. Y'all are going to do great, and I will talk to you then.